in the conference a recent a workshop on recent advances in computational linear algebra, nonlinear functions, nonlinear equations, and simulation 2022. I invite our respected Dean Sir, Professor N. Arunai Nambira Sir, to proceeding for this conference. So, over to
Yeah, thank you, sir. So on behalf of School of Advanced Sciences, Department of Mathematics, I welcome you all for this one-day workshop on recent advances in computational linear algebra, matrix functions, nonlinear equation and simulations 2022. I welcome the speakers, Dr. Fasula Soleimani, Institute for Advanced Studies in Basic Sciences from Iran. Welcome you, sir. I also welcome the other speakers, Dr. Munish Kansal from Thapar Institute of Engineering and Technology, Patiala, Dr. Svetab Srivastava from CMP Degree College, Central University of Allahabad. I thank you all the speakers for joining and giving your valuable time and insight for our scholars and our faculty, sir. Thank you very much. So just to have a brief introduction about our school, SAS. The School of Advanced Sciences was established in the year 1984, comprises of mathematics, physics, and chemistry departments. The vision of the school is to provide quality teaching and high-level research to make impact at the global level. The school consists of experienced, enthusiastic, energetic faculty of strength 235 so far. We have 118 in mathematics, 45 in physics, and 72 in chemistry. The school offers master's program, MSc in data science, business statistics, physics, and chemistry with specialization in analytical, inorganic, organic, general chemistry, also in pharmaceutical chemistry. The program includes full-time 6 months research-based capstone project in the 4th semester. The school also offers integrated Master of Science in Physics, Chemistry, and Mathematics, and computational statistics and data analytics. So the school also offers PhD program in frontier areas in physics, chemistry, mathematics. The candidates are for PhD are selected through a common entrance test and interview. The school has on roll so far 750 PhD scholars, includes both part-time and full-time. So the subjects of chemistry and mathematics in VIT are ranked at 401 to 450 and 451 to 500, respectively in QS World Ranking in India. So with this brief introduction, I welcome you all for this wonderful workshop initiated by Dr. Hemant Kumar. I thank our head of the Department of Mathematics, Dr. Karthikeyan, for all the initiative is taken to improve the quality of teaching and research in the Department of Mathematics. I also welcome the participants, our own faculty colleagues, research scholars, and other external participants for this one-day workshop. Definitely this workshop will take to future collaborations in terms of paper publication and joint funded projects. Welcome you once again. Thank you once and all. Thank you very much, sir.
thank you, Arunai Sir. I invite our HOD Mathematics, Dr. K. Karthikeyan, to introduce the speaker. Over to you, sir.
Thank you, sir. Respected Professor Arunai Nambiraj, Dean SAS, keynote speaker, Dr. Fasula Soleimani, from Institute for Advanced Science Studies in Basic Sciences, Iran, my faculty colleagues, convener Dr. Hemant Kumar Nashine, and all participants. Very good morning to one and all present here. I would like to introduce our keynote speaker, Dr. Fasula Soleimani. Just a few minutes. Dr. Fasula Soleimani has completed his BSc degree. One second. BSc in Applied Mathematics from University of Sistan and Balochistan, Iran, and MSc in Numerical Analysis from Islamic Azad University, Iran, PhD from Ferdowsi University of Mashhad, Iran, and postdoctoral fellow from Institute for Multidisciplinary Mathematics, Polytechnic University of Valencia, Spain. And sir is working in the Department of Mathematics, Institute for Advanced Studies in Basic Sciences, Iran. He has published 115 research articles in refereed journals and 10 articles presented in various conferences. The citations in Scopus is 1362 and H-index 23. Now, current area of research sir, is computational mathematics, stochastic computing, iterative methods, applications of machine learning. I welcome our guest speaker for this wonderful workshop, and thank you one and all the participants here. Thank you, sir. Thank you.
Yeah, thank you so much for the introduction, sir. Thank you for valuable time to Darunay sir and Karthikeyan sir. So in front of us, we are having all the three speakers, Dr. Solomani sir, Dr. Svetab, and Dr. Muniz. So yeah, thank you for joining and accepting invitation. I would like to say the Solomani sir to start your talk. I think now. Are you ready, sir?
The other two speakers, yeah. Dr. Svetab Srivastava and Dr. Muniz Kansal, for this workshop. Thank you for your time, sir. Welcome you.
Yes, yeah, sir. Thank you, sir.
So Dr. Munish and Svetab, we are having the Dean, Dr. Arunai Nambiraj, and the K. Karthikeyan doctor, and this is he is a HOD of the department.
Good morning, sir.
Hello, sir.
Hello, sir.
Welcome, sir, all of you.
Thank you so much. Thank you so much.
Okay, so now over to the Solomani sir. I think you can start your talk.
Okay, thank you so much. So can I upload my file now?
Yeah.
Okay. And I think it's better for me to turn off all of the incoming videos.
Yeah. Even other participant video are off. I make it possible. And so other Svetab and Munish also can do. If you want to off, they can do.
Okay, so can you see my screen now? Can you see?
Yeah.
Because I just uploaded the PDF file in order to present it.
Yeah, absolutely fine. We can see.
Okay, so is the size okay? I mean, the font size is okay?
Yeah, I think okay. So Svetab, this is fine, right?
Yes, it's fine.
Yeah.
Okay, and do you have my video before starting?
Yeah, that is I can see. Yeah.
Okay. So thanks for having me in this workshop, and I'm really happy that finally I made it in order to come here and give a talk in the field of numerical linear algebra. It was not that easy under the current situation in order to prepare the talk and the slides and stuff like that. But finally, with the help of my colleague Hemant and the other ones, I was able to prepare the files and made it in order to be in this conference. Before starting the talk, because this is actually a workshop, I want to remind you that I prefer not to have a one-way talk. So even in the middle of the talk or after a couple of minutes, wherever you want, so you can ask your questions. Unfortunately, I cannot see the chat box right now next to my screen, and I think the organizer, Professor Hemant, will help me out in order to let me know if any of the attendees have any types of questions. Yeah, I also try to pause in the middle of the talk and invite you to the session in order to ask your questions to have a fruitful discussion.
Yeah, so yeah, I want to pause you, sir. Yeah, so when you think you can ask the question, so on that time people will raise the hand, and one by one I will call to them to ask the question. So that will be better.
All right. Please just tell me If someone asks a question, please just tell me, and we can stop and answer to the question in order to have fruitful discussions. Okay?
Okay, fine. Thank you.
Thank you so much. And if something happens for the internet or stuff like that, just let me know as well in order to repeat my sentences.
Okay, fine. Thank you.
All right. So today's talk is about an introduction to matrix functions. So I decided to talk about matrix functions because, you know, functions of matrices have so many applications, not only in terms of theoretical aspects, but also in practical applications. When you face, for example, with some special differential equations or some other practical problems from engineering, we need to tackle functions of matrices. And because of that, I prefer to talk about matrix functions. What are matrix functions? And then we will talk about some iterative methods and some theoretical concepts about functions of matrices, and introduce a new iterative method. We will focus on it, try to talk about its theoretical aspects, its convergence and its rate of convergence, as well as some practical things. Okay. So the overview of this talk is, as you can see, is about introduction. After introducing the topic shortly, I will move to talk about some standard techniques and methods in order to compute functions of matrices. Some of the techniques are of theoretical natures, and some of the techniques are from computational nature. So we have to understand them and use them in appropriate places. There is an important question that I will answer in the talk. The question is about why the computation of matrix functions is important. Why is it important to compute functions of matrices? When do we need them? Where do we need them? After that, I try to point out some connections between some of the matrix functions. Later, I will talk about iterative methods and the numerical procedures in order to find matrix functions. Especially, I will focus on matrix sign function. I will tell you why. The sign function for matrices is quite important for us because it has a close relationship with the other types of matrix functions. And if we can propose a good method for matrix sign function, then we can use it, we can extend it to compute other types of matrix functions. Then I will talk about the types of convergence, because when we talk about matrix functions and we want to, provide and propose some matrix iterative methods, we're not anymore talking about scalar convergence. We are talking about matrix convergence, and we have local and global convergence, and we have to understand these things. The rate of convergence is another subtopic that I will talk about. After that, I will talk about the stability of iterative methods. You know that, okay, let me, okay. You know that iterative methods that are stable are much more helpful for us in practical problems rather than the unstable ones. And at the end, I try to provide some numerical simulations. Okay, the history. Functions of matrices have been studied a long time ago. you know, as long as matrix algebra itself. As far as I know, the first person who talked about matrix functions was Kiley, who tried to compute the square of a matrix. We know that how to compute the square of some numbers, of some scalars under some conditions, for example, for the positive or negative scalars. But how could we compute these these functions for matrices? That was the first question that came to the mind of Kiley so many years ago. And after that, it was Sylvester, another famous mathematician in the field of numerical linear algebra, who provided a general perspective and definition for matrix functions. After that time, research in the field of matrix functions in any directions developed. For example, in the field of this theory of matrix functions, the numerical analysis of matrix functions, you know, the application of matrix functions in other fields. And you know, so some people, for example, they want to propose some algorithms, or they develop some software codes in order to employ matrix functions for practical problems. That's another research line. So a lot of research lines after that time had been coined in this field, and it has been moving on even today. What is a matrix function? A matrix function actually transforms a matrix to another matrix of the same size. So if you have a matrix, for example, of the size n by n, then when you impose a matrix function on it, you will obtain another matrix of the same size. But it must satisfy certain conditions, certain criteria. An example is helpful for us for clarifying the situation. Please consider that you have the square root, the simple square root function. F of t equals the square root of t. So the question is now, what is f of a when a is a 2 by 2 matrix? This is a simple question that came to the mind of Kiley more than a century ago. Another question now is that what's going on and how can we tackle the computational matrix functions when the size of matrices grows rapidly? For example, you will face with the matrices of the size 100 by 100 or 1000 by 1000, 10,000, 100,000, or sizes like that. So it is important for us to find good procedures, I mean theoretical methods or numerical methods in order to compute the matrix functions, the associated matrix functions. For example, in this case, the square root. And another thing which I want to draw your attention to is nonlinear matrix equation. There are a couple of nonlinear matrix equations that you may face by now in your life when you study mathematical papers or robust mathematical books. You have faced until now with a couple of nonlinear matrix equations, such as number 1, x to the power of 2 equals I. Hemant, is there any questions? Or I could go on.
No, there is no question.
Okay. So x to the power of 2 equals I. I is the identity matrix of the appropriate size. So what is the solution to this matrix equation? The solution to this matrix equation is called a matrix sign function. Another one is equation number 2. X to the power of 2 equals A. X and A are appropriate matrices of the same dimension, and under further assumptions that I prefer not to talk about the assumptions right now. Maybe later I will talk. So the solution to the nonlinear matrix equation 2 is a matrix square root. So are there anything else? Let's see. Matrix exponential. Actually, the matrix exponential is the solution to the nonlinear matrix equation 3. So I'm trying to draw your attention in order to see the mathematical formulas that you have seen by now, not anymore in the Scholar format. What if you see them in the matrix format? Are they valid in the case of matrix format? This is the question. And based on this question, you can define the appropriate functions of matrices. Number 4 is matrix cosine. So you all know about the sine and cosine functions more than me. But how can we define a matrix cosine? How can we find a matrix sine functions? So a matrix cosine function is a function that satisfies number 4. Something came to my mind just right now. For example, in the Scholar case, we all know that the sine of x to the power of 2 plus the cosine of x to the power of 2 is equal to y. Can we see a similar thing for the matrix functions? So if we know about the theoretical things, if we know about the concepts of functions of matrices, we can say yes to this question. The matrix sine of x to the power of 2 plus the matrix cosine of x to the power of 2 is equal to the identity matrix always. Of course, I'm talking about these formulas in the exact arithmetic or in IEEE arithmetic format, and I try to ignore the round off and cancellation errors, because sometimes if you consider those errors in your calculations which come from programming, then sometimes these identities will not be equal to each other, but in exact arithmetic you can see and under further assumptions. So another point that I want to say is that, okay, up to now I said some concept about functions of matrices and a short perspective about matrix functions, but we need to be more careful when we talk about the solutions. In particular, the possibility remains that there are solutions X that have a spectrum of the form required for primary matrix functions. What does that mean that I wrote up there? It says that in the Scholar case, for example, you have one solution, two solutions under different criteria. But for the matrix case, in matrix environment, it's not that easy to say that there's only one solution. Of course, we try to focus on primary matrix functions, primary solutions. Primary solutions are the solutions that they can be expressed in 3 different formats according to the definitions of matrix functions that I will say after a couple of minutes. But sometimes there are some matrices that can satisfy on the matrix equation, but they are not primary. So we must be quite careful when we, when we move from the Scholar environment to the matrix environment. This is quite important, and we must be so much careful when we do this transition. Another thing is that one matrix function generates or provides the need for another one. For example, when we talk about matrix exponential, this shows that sometimes we need to compute the logarithm of a matrix. So there is a a transition between the logarithm of a matrix and exponential of a matrix, as well as there is a transition between the sine of a matrix and the cosine of a matrix, the matrix sine function and the matrix square root, etc. So there are the point is, when we define one matrix function, it also shows the importance of another type of matrix function. Here, before going on, I want to recall about another thing. When we talk about matrix functions here in this talk and in our papers or research, we do not mean element-wise computations. For example, in some books or some works, you will see that when we write down the exponential of a matrix, that means that you compute them element-wise. We do not refer to that case. When we say about matrix exponential, we mean the solution to a nonlinear matrix equation 3. And we're not referring to the element-wise definition. Okay, what else can we say here about functions of matrices? What are the simplest functions of matrices? Okay, as you already guessed by now in this talk, the simplest functions of matrices are the following two ones. Matrix polynomial, it's quite popular. For example, a to the power of 2 plus a to the power of 3. I'm talking about matrix powers. And the matrix inverse, number 6, it's very challenging. Maybe you haven't thought about this yet in your research career. You can see the matrix inverse as a matrix function. Actually, one of the simplest matrix functions in this field is the matrix inverse, which is the solution to the nonlinear matrix equation 6. So, another important thing here is that there is a close relationship between iterative methods for solving nonlinear scalar equations and matrix functions. At first sight, when I say this sentence to many of my colleagues or students in the talks, they say iterative methods for finding the solution of nonlinear equation. That's an old topic, and sometimes it's not that challenging. But I say that is, and that could be helpful if you want to know more about the theory and applications of matrix functions and practical problems. For example, when you find an iterative method for the solution of nonlinear scalar equation 7 and you want to find a simple zero under a couple of conditions, you can extend your method in order to solve the previous nonlinear matrix equation. For example, number 1, to compute a matrix sine function. For example, number 2, to compute a matrix square root. Another instance is about 3, to compute matrix exponential. However, here I want to clearly say that this transition from the scalar to matrix environment is not that straightforward. You should be sharp when you do this transition in order to have the stability of the iterative methods.
Yeah, Faisal, I want to
Yes.
pause. I think one query, somebody is raising the question, hand. Harish sir, Professor Harish.
Please ask your question.
Yeah, you are raising question. Any question from your side? Mallika Ranjan sir, Harish Mallika Ranjan sir. I can't hear you.
Okay.
Okay, okay. Okay, Faiz sir, you can continue because voice is not coming from there.
All right, no problem. So please try to ask.
Can you hear me now?
Yes, sir.
Yes. Sir. Okay. Question 6. What is the matrix A? Equation 6. Sorry. Is it a constant matrix or what is it?
Can you repeat your question louder?
Oh, okay. Louder. Equation 6. What is the matrix A?
What is matrix A? Okay. What is matrix? I already told you, X and A are two matrices of appropriate sizes, and if you solve, the nonlinear matrix equation 6, then you will obtain X. X would be, uh, the inverse of matrix A. Okay, is that okay?
Okay. X is the inverse of matrix A.
Yes.
Okay.
Okay. Anything else?
Yeah. Okay. Fine. Fine.
Thank you. Thank you. Can I go on?
Yes,
Hemant,
sir.
can I go on? Hemant, can I go on?
Yeah. Sweta, you have question.
Yes, sir. Hello, sir. Professor Faiz, sir. Are you listening me? Am I audible?
Yes, please speak louder, please.
Oh, okay. Now, am I clear? Am I audible to you, sir?
Yes, please go on.
Okay. So this question is about the equation number 6, where you have written matrix equation fx equal to x inverse minus a equal to 0. So I have just one query related to that. I mean, so can we apply like Newton-Raphson's method to these matrix equation? Because in generalized inverse theory, I have seen Newton's iteration method. Okay, I hope that equation came by applying Newton-Raphson method to this particular function. Is it possible, like those Newton's Raphson method that we apply for nonlinear equations, can we apply those methods to the matrix function equation also, right?
Okay. If I understood your question, I have to say that your question is a very good one. The answer is yes, but as I told you 2 times up to now, you should be quite careful when you impose your Newton's method, your iterative method from the scalar environment to the matrix environment. Because sometimes we do not have the matrix, we know that matrix multiplication is not commutative. We should consider this feature in our calculation. If you consider this, then we can impose the Newton's method, Chebyshev method, or the other ones that you know maybe better than me in order to solve 6. And the best way is to consider 6 in the scalar case. So you can consider f of x in number 6, with small letters. I mean, if of a small x equals a small x to the power of -1 minus small a. For example, you want to compute the inverse of a scalar a. Then you have to impose your Newton's method. After severe simplifications, yes, you will obtain a method. I think you will call that method as Scholl's iterative method. And under a couple of conditions in the initial matrix, you can convert to the matrix inverse. And the other thing is that matrix inverse is the simplest thing that I just wrote in number 6. In the most general case, you can compute generalized inverses based on number 6. You can compute the Morgan-Rose inverse, the weighted Morgan-Rose inverse, the Draisine inverse, the weighted Draisine inverse. the outer inverses, the two inverses, the one inverses, all of these inverses which have their domains of validity and usefulness can be computed by iterative methods. But we must be sharp when we impose our iterative methods. Is that fine until now? Can I go on?
Yes, sir. Yes, sir. Of course. Thank you so much.
Okay. Thank you. Okay, so let me go on. Hemant, thanks for your help.
Yeah.
Thanks for your help. Okay, so I already talked about the concept and the perspective, the origin of matrix functions. But are there any formal definition in the literature in order to define matrix functions? Yes, there are three formal definitions. The first one is the Cauchy integral representation. You know, if A is an n by n matrix with complex entries, then the f of A, which is a matrix function, can be computed and represented by the Cauchy integral, as you can see in number 8. This integral is quite, you know, it's quite special because you have to define it, you know, on the eigenvalues of the matrix A. It should be contained in the domain of analyticity of A. And we call it sometimes the Cauchy integral formula. Okay, but what about the others? We can also define matrix functions with the Hermite polynomial interpolation and also with the Jordan canonical forms. These three definitions are quite popular and they have some theoretical natures. If you want to find a matrix function, theoretically, you can use one of these trees. But I provided the comments at the end of this slide. You know, the point is the other definition, all of these three definitions, the Cauchy integral, the Jordan canonical forms, or the Hermite polynomial interpolation, in order to define your, you know, your matrix functions, are equivalent. And I will give you one solid reference later in this talk that you can see valid and robust proofs in order to show that these three representations are equivalent. Features. Okay, so now you can consider that you have a scalar function f in a matrix A in the complex environment. Can we say anything about the features of f of A? We have the size of A. So the first thing that we can say is that A and f of A have same dimensions. What about the others? Are there anything else? Are there any other features that we can say in general for matrix functions that we can use later in our calculations, in our theorems and proofs? Yes. If you define the function f on the spectrum of A, on the set of the eigenvalues of A, then for the matrix function f of A, you can say that f of A always commutes with A. This is an important feature. F of A commutes with A in the exact arithmetic, of course, and vice versa. F of A transpose is equal to its transpose of f of A. The third one, which is very helpful in Jordan canonical form, is that the f of xa x inverse equals x f of a x inverse. This helps us when we, you know, use Jordan canonical form to prove the convergence of iterative methods or stuff like that. If you have the eigenvalues of the matrix A, then the eigenvalues of f of A are f of lambda i's. So this is another transition that sometimes helps us, especially when we solve, practical problems, and we want to talk about the stability of our solvers. And then the last one is somehow similar to the first one. If X commutes with A, X is another matrix in this case. For example, you have a matrix B of the same size, of an appropriate size, and it's, commutes with A. Then f of A also commutes with X. This is also important for us, that we will use also in this talk. This is the part that I want to focus on, and I want you to be more careful and pay close attention to this slide and maybe the next one. Why do we need matrix functions in practice? Okay, there is an extension generalization from the scholar to matrix case. Why do we need them? I just provided 2 examples here, and I try to tell you a couple of other ones that will illustrate the importance of matrix functions. Please consider a second-order matrix differential equation, number 9. This is a second-order, differential equation, and under appropriate initial conditions, you can solve it. But if this differential equation is a matrix type, I mean here A in number 9 is a matrix. For example, this is a 100 by 100 or 1 million by 1 million matrix. How can you solve it? We know that the exact solution to number 9, according to theoretical procedures to find the exact solution, can be represented by number 10. So in the solution 10 for number 9, you can clearly see that we need to compute a lot of matrix functions. We have to compute the square root of a matrix, the inverse of the square root of a matrix, the sine of a matrix, and the cosine of a matrix. 4 functions of matrices must be computed in number 10 when in 9 A is not anymore a number, it's a full matrix. And this shows that it is important for us to know about matrix functions, to develop the theory and the theoretical methods as well as the numerical methods to compute matrix functions. Are there anything else in literature about the importance of matrix functions? Before saying that thing, if you paid close attention in the previous slide in number 10, you can see that here we need to compute the square root of a matrix. Because of that, I prefer to provide a theorem here. We have a popular identity in the theory of matrix functions that interlinks the sine function and the matrix square root and its inverse. If you can see to number 11, equation number 11, when you have an appropriate A of the same of an appropriate size and with appropriate eigenvalues that I will tell you later in this talk, the sine of that block type matrix would be equal to block type and matrix in the right side, which contains the square root and the inverse square root of a matrix. And this another time shows that the computation of sine function is important for us. Here, if we can compute the matrix sine function, then based on some identities and some formulas, we can compute the other types of matrix functions, which are quite important for us. Another motivation which is very important for us, is the application in stochastic differential equations. Maybe some of you know about the stochastic differential equations of E2 type. You now please consider a system of E2 STEs in number 12. Okay, in number 12, as you can see, we have a Wiener process, which is actually an n-dimensional Wiener process. We have a drift term F and the diffusion term G, which here is a square root of a matrix. Here, the diffusion part, okay, in the second part of the right side, is a to the power of 1 over 2, which is applied to a vector or to a function. This itself says that the diffusion part is a matrix function. So how can we solve number 12? In practical application, most of the time A is a symmetric matrix. However, now I'm trying to focus on the general case. T is time and it's changing. For example, T is from 0 to 1 year, and you want to know about the solution to a system of stochastic differential equation. How can you solve it when the coefficient here is a matrix function? If we want to talk about this important application here for you, you can consider a grid on the time which contains n+1 nodes. So the nodes could be, generated uniformly or non-uniformly. Here I consider that for the sake of simplicity that the time step is uniform. So you have the grid 13. Then you can employ the well-known Euler-Maruyama method in order to solve your stochastic differential equation. If you remember from the stochastic environment and the stochastic courses or papers that you studied up to now, so the Euler-Maruyama method to solve the stochastic differential equation with a random source would be written as 14. So in 14, you can clear the entries of a matrix A are changing by time in each time step, and in each time step you need to compute one matrix square root. So if you consider that you want to solve it with 1001 nodes long time, then there would be 1000 steps. So for 1000 times you need to compute this matrix function. So it's important to drive new methods which are efficient and can be employed in order to solve practical problems, especially in a stochastic environment based on matrix functions. Here at the end, I just want to tell you that the n is a normal variable of mean 0 and the variance 1. Okay, let me go on. If you don't have any questions up to now, I will go to the next slide, and if you have any questions, just tell me now, please. In this slide, I try to talk about this application further. You can consider that here we have equation 17. This is a system of stochastic differential equations. This is a well-known model, which is a stochastic Lotka-Waltrop-Predator-Prey model. As you can see in the second part of number 17, we have to compute the square root of a matrix. Each of xt1, xt2 are stochastic processes from now on. So they are not anymore, deterministic functions, just like the deterministic differential equations. Here, dw1 and dw2 are two white noises, which have been obtained based on independent Brownian increments, as you can see at the end of the slides. I just programmed solving this equation number 17 with the help of the Euler-Marioma method and computed the matrix square root, I think, with the theoretical methods. And you can see the solution here. So x1 and x2, the solutions have been plotted here in this figure. You can clearly see the randomness and the noise in the solution. And the point is, when you want to obtain this solution, you need to compute a matrix function at each time step. That's an important thing that I wanted to tell you. And because of that, the computational matrix functions is important. So now I just stop here for 1 minute. If any of the attendees have any types of questions until now, please just let me know.
Yeah, if any participant have any question, you can raise your hand. So I think Faisal, you can continue. There is no question till now.
Okay, all right. Okay, so until now, I pointed out the origin and perspective of matrix functions, the formal definition of matrix functions, and the relation to some nonlinear matrix equations. And I try to provide some features for matrix functions and some practical applications. Let me move one step ahead and talk about one of the most important matrix functions, which is the sine function. I'm sure that you know much better than me that the sine function for scalars can be defined via 18. Just take a look at equation 18. Sine of z equals -1 when the real of z is less than 0, and when the real of z is positive, the sine of z would be 1. This is quite, straightforward, and you know that. I have a question now. How can we define this function for square matrices? How can we extend this definition for square matrices? Here, I try to provide the Jordan canonical form definition for matrix sine function. You consider that A is an n by n matrix which is not 0 and it has complex entries, as well as it doesn't have any pure imaginary eigenvalues. It doesn't have any eigenvalues which is located on the axis of imaginary. So you can clearly write down the Jordan canonical form in 19, A equals Z, JZ inverse, at which J is a block type matrix that consists J1 and J2. J1 and J2 are the Jordan blocks, which contains the eigenvalues which are located in the left and right half planes of the complex plane respectively. So you can define the sine of A with the help of Jordan canonical form easily with number 21. Sine of A would be S, which is equal to Z times by that diagonal matrix times 2 is the inverse. Here, P plus Q would be N, would be the size of the input matrix. And the point is, we define sign of A, the sign of a matrix, only for non-singular matrices. Because if you want to compute it, there shouldn't be any eigenvalues on the axis of imaginary. This is one definition. So if you want to define it based on the Cauchy integral representation, you can similarly define. So these are the theoretical definitions. So as you know, most of the times, there are some restrictions in the application in the applications of theoretical methods. For example, when the size of the matrices are high, it's sometimes different to compute the matrix function via theoretical methods. Or, just like the previous example that I showed you for the stochastic differential equation, for some matrices, the entries of the matrix is changing a long time. In such cases, if you compute the matrix function at the beginning, after that, with the help of iterative methods, only when 1 or 2 iterates, you can compute the matrix function. It's not necessary to build up the solution with the theoretical methods for each time level. So it's sometimes important to focus on iterative methods. That's the topic that we try to move on in the next slides. Before that thing, I want to recall 2 more important things. Just like in the theory of matrix functions, just like matrix algebra, that we have a couple of decompositions, such as I don't know, the LU decomposition, the Cholesky decompositions, or the other decompositions. Sometimes we can decompose matrices with the help of matrix sign decomposition in number 22, which are useful in a couple of applications. Another application that I just provided here shortly, and you can see, in my papers if you want to know more about, is the way of finding the solution to special nonlinear matrix equations with the help of sign function. Some of these matrix equations are the Riccati matrix equation, the algebraic Bernoulli equation, the algebraic generalized Bernoulli equations. In all of these nonlinear matrix equations, you can use an iterative method, such as the Newton's method or the similar ones, with the help of a matrix sign function in order to solve your problem. The only thing here is that sometimes in order to construct your procedure, in order to solve the Riccati equation or the nonlinear matrix equation like that, you need to use tensors. Tensors are used here in this context in order to solve nonlinear matrix equations. Okay. Iterative methods. The most fundamental method here in this category, in order to find the solution to some nonlinear matrix equation as well as some matrix functions, is the Newton's method. So Newton's method here, in order to compute the matrix sign function, can be written as 23. So if you say how we obtain 23, you have to consider in your mind the nonlinear matrix equation that I showed you in a couple of slides ago. Let me just quickly go back and show you because it's important. If I go back to equation number 1, if you impose Newton's method in order to solve number 1, then you can obtain number 23. This is Newton's method. So it converts to the solution under some conditions. For example, the initial matrix must be matrix A. Another type of methods which are very important for us are the Padé approximate, or the methods that obtained by Kenny and Lobb in their fundamental paper, which are based on Padé approximations. You know about the Padé approximations, which are some rational approximation to some functions. Here, if you consider number 24, and then you can consider a Padé approximation of M and N. M is the is the power in the numerator, and N is the power in the denominator of 25 approximation. So so actually we can find a general family of iterative methods which are known in literature as Kenny and Lobb, or Padé approximation methods, that could be written as 26. The most important thing is here. Maybe at first sight you say that, okay, so Newton's method have already been applied. Let's think about the other methods. All right, but if you want to think about the other iterative methods in order to impose them for solving and finding some function, you must be looking at methods quite new in methods, a family of iterative methods. The Padé family of iterative methods will be convergent with a rate of convergence m plus n plus 1. So with this rate of convergence, they converge to plus minus, plus minus 1. Let me just go on and then have your questions if you have any. Newton shows iterative method. Number 27. It can be written and can be used in order to find the sine function. Halley's method, 28. If you can consider the Halley's method of solving nonlinear equation, if you consider it to find a matrix sine function. All of these methods are special cases of the Padé family, 26. So you must be quite careful. The another thing is about the reciprocal of this family. 26 is a family of iterative methods to find matrix sine function. Its reciprocal is also another matrix iteration that could converge to plus minus 1 and can be useful to compute matrix sine functions. Do you have any questions until now? Because I thought someone was going to ask a question. Hemant, is there a question until now?
Any question? Yeah, you can ask the question, Dilan Ahmed.
Okay, thank you. Equation number 26 converts to 1 or minus 1 because we have a sine function.
Yes, exactly, because we're talking about sine function, exactly. And we constructed this method in order to solve 24. Yes, you're right. And that is the point. We have to we have to construct an iterative method that converts to plus minus 1. I will show a figure about this later in this work. Thanks for your question. Okay, let me go on.
Yeah, so, Saurabh, you have a question.
Yes, please.
Sir, there is one fundamental question I have, that suppose we are considering a quadratic equation, non-polynomial equation, x square plus bx plus c is equal to some 0. So when we are considering the matrix equation and of the same type, So how does it change the geometry of this equation? This is one I'm very curious about this geometry. How, like, I can figure that this is a polynomial equation. This is the path of this. I can plot in the graph. So is it possible to plot or think of a matrix equation and its geometry? Thank you, sir.
Okay, so as you told me, your question is about the fundamental background of this process. First of all, I want to repeat that the procedure is not simple. Just to use a method that you already used for a scalar case and you extend it for the matrix environment quite easily. That's not possible. You need to impose a lot of conditions. This is the first thing. The second thing about the geometry of it, you can provide, you cannot plot the solution as in the way that you plot the solutions for the scalar case. Third part of my answer is that if you want to understand a geometry of the solution, you need to be able to define the derivative of a matrix quite well. That is the most important part. So, if, for example, you can say that I want to employ the Newton's iterative method in order to solve my general quadratic matrix equation. All right, it's possible, but how do you define your derivative? The derivative in this case must be defined based on special matrix Frechet derivatives. So if you define the Frechet derivatives for matrices quite well and in general format, then it's possible to move from the scalar environment to the matrix environment in order to solve your question. Okay. Hemant, if there isn't anything else, I will move on.
Yeah, this is fine, Saurabh.
Yes, can I go on?
Yes, sir.
Yeah.
Sure.
Okay.
Okay, thank you. There is another thing that I provided here in this slide because I thought that it's important for us, and it's about the history. You know, after I think 1 decade that Kenny and Loeb provided their iteration formula 26, I think it was Bruno Iannazzo, an Italian mathematician, possibly around 1 decade ago, 10 or 12 years ago, that he found that even these Pade approximation methods could be obtained with the general conic family of iterative methods. If you know about iterative methods to solve nonlinear matrix equations, there is a family of methods that we call conic family, that obtained by Schroeder possibly around 1 century ago, more or less. If you employ that method in order to solve your specific scalar equation x to the power of 2 minus 1 equals 0, then you obtain a family of methods which are the Pade approximation methods. So actually here I want to also say that sometimes you can obtain one method with 2 different ways. Another thing is that here I provided table 1. One table I provided here. Why I provided? Because I wanted to tell you that you can construct a lot of methods with the family of iterative methods of Pade, but only the m and n and m minus 1 over m Pade approximates are globally convergent. This is a term that I want to talk about later in this talk. Let me, if I can focus, I hope you can see the table well. You know, for example, when m equals 1 and n equals 1, then you obtain a global globally convergent method. When m equals 2 and n equals 3, this one that I'm trying to show you with, I'm sorry, this one that I'm trying to show you with my mouse, this is globally convergent. So the point is, the bottleneck is that none of the, sometimes some of the methods in this table or from the Paddy family of methods are not useful in practice. Some of them converge globally and some of them converge locally. Okay, let's go on and talk about this more in details. Very recently, I think me and some of my colleagues a couple of years ago, I think 4 or 5 years ago, we proposed a Chebyshev-Halley type family of iterative methods for computing the matrix sign function S in number 29. You can clearly see that in number 29 there is a free parameter. This free parameter is helpful. So under some choices of A, we can obtain the already developed methods, and under some choices of A, we can obtain some concrete cases which are quite new. But here the question is, how can we improve the convergence order as well as the computational efficiency of number 29? So one more time, we have to solve the nonlinear matrix equation 30, which I showed you a couple of slides ago. So in order to solve number 30, you have to propose a suitable iterative method in the scalar environment. I didn't say that an optimal method. I didn't say that an optimal with memory method. I said that you have to propose a suitable iterative method. You will see that why. Okay, so the construction, as I already told you a couple of times, is that we have to solve equation 30 with your iterative method. But two things are important, are quite important for us when we want to design new methods for matrix sign function. The first one is that the matrix iterative method that we obtain must be new. It means no one else proposed it by now, and it doesn't belong to the Paddy family of methods, or its reciprocal. So it must be new. And the second important thing for us is that this proposed method must be globally convergent. How can we check that? How can we say about the global convergence? What is the meaning of local versus global convergence in order to compute the sign function? We're not talking about solving nonlinear equations in general format. Here we just focus on the sign function. Okay, this is a three-step method. Okay, which is based on the Chebyshev-Halley method, at which A is a real number, and we defined this iterative method based on two divided difference operators. So if we use this method in order to solve that nonlinear matrix equation 30, then we can obtain an iterative family of methods, iterative methods. Here, let me point out some important things. If you are an expert in the field of iterative methods for solving nonlinear equations, you will say that 31 is not an optimal method. It doesn't reach the highest possible convergence order with the minimal use of functional evaluations. All right, we all know about this. But the important thing is that when we impose 31. In order to solve 30, we should finally obtain a structure which is efficient for us. This efficient means that that structure does not require the square root, does not require the sine function, does not require other types of functions. And it is not that costly in terms of matrix-matrix multiplications. And because of that, we must be so much careful when we use and employ an iterative method in order to solve our matrix equation. Okay, about 32, we all know that if f is a sufficiently differentiable function around the simple zero, then if you consider the initial point x naught quite close to the simple zero, then the structure 31, I'm sorry, this iterative method has convergence order 6 in order to solve nonlinear equations, and it reads the error equation 33. Okay, this is quite simple, and I didn't provide the proof here. Okay, let me go on. So after applying this method 31 on the nonlinear matrix equation 30, we obtain 34. So 34 is an extension over the method that me and some of my colleagues provided some years ago. It has one free parameter that is helpful for us. And as you can see, in this structure, we have the identity matrix, we have matrix powers to 2, matrix power to 4, 6, and 4, and here also to 2, 4, 6, and 8. And we have to compute one matrix inverse in each iterate. Only one matrix inverse is required at each iterate in order to move on. Okay, are there any questions until now?
Is there any question? Please raise your hand. No, sir. At the moment, there is no question.
Okay, let me just go back. Okay. So, after the talks that I had until now, I constructed an iterative method for solving the sine function. This iterative method, just like the other iterative methods, converts the solution to the sine function only if the initial matrix is chosen appropriately. Hopefully, in this case, we have a very good choice at hand, and you will see later in this theorem. Let me tell you this theorem and then go on to the convergence analysis. This is a theorem that interlinks the computation of matrix sine function and matrix square root. It says that let A have no eigenvalues on the left hand side of the complex plane. And if you consider x naught as 35, then you will convert to 36 with the previous iterative method for solving matrix sine function. And at the end, you obtain the matrix sign of a block matrix, which corresponds to some blocks at which any of those blocks are the square and the inverse square root of a matrix A. Okay, let me go on to the concrete cases, and after that to the convergence analysis. All right, if you consider A equals 0, you obtain a method. So for any choices of the free parameter A in our family of iterative methods, we can obtain one iterative method. So this shows the generality of our method. of our procedure. So we obtain PM0, PM1, PM2, PM3, and the other ones. Here you may ask that which one is useful? This is a very good question. Which one is useful for us? I already tried to mention something about this. These methods are useful as long as they are new and they are globally convergent. These are the first two things that we have to check and important for us. After that, we need to pay close attention to the convergence order and to the to the cost of our matrix method. So for some other choices of this family, we can obtain PM6, PM7, PM8. I provided these things because they are important for us. For example, if you choose A equals 1, you obtain PM8. The structure of PM8 is obvious, okay, in 46, I'm sorry, in 43. Sorry, I made a mistake. But the question is it useful for us? Let's see. Let's see more. Local convergence versus global convergence. The best way in order to check the convergence behavior of our iterative methods in order to find matrix sign functions is to employ the basins of attractions. As you probably know, attraction bases are the procedures at which you consider a rectangle in the complex plane, then you discretize your domain by some points, nodes of your domain, and you check that your node, your point in the domain, converts to root number 1 or root number 2. According to the root that it converts to, you will assign a color for that root. In this procedure, you will obtain the attraction basins associated to iterative methods for solving nonlinear equations. So let us consider the previous iterative methods that we obtained for various cases of A. In order to solve f of x equals x to the power of 2 minus 1 in this color case, and in the domain of minus 2 to 2 multiplied by minus 2 to 2 in the complex plane, and let's see what would be the results. These are the attraction basins. Unfortunately, I cannot zoom here in this software. I'm sorry about that. I hope you can see the figures with good qualities. So you can see that the attraction basin for the Newton's method in top left. After that, PM8 in top middle, and in top right we have for Padé iterative Padé method 3-4. 3-4, so the family converts, the method converts globally. So here you can understand the meaning of global convergence. If you take a look at the attraction basins, you cannot see any black area in the figures, except the points which are located in the imaginary axis. Okay, the roots have been shown by white colors, and the green and the blue area are completely different to each other. Another important thing here is about the shades. We have a couple of shades. Around the root, it's lighter. When you move away from the roots, the colors would be darker and darker. This shows the convergence rate of the iterative method. The Newton's method converges with the second order of convergence, but PM8 converges with the higher rate of convergence. And as you can see, if you consider any point in one area of the green area, for example, in top middle figure, then with one iterate, you converge to the solution. If you move ahead and go to the second layer, with two iterates, you will converge. If you move further and go to the third layer, with three iterates, you will converge to the root. And personally, I also want to say that PM8 area of convergence are lighter and they are larger than the areas for convergence of 3 and 4 pad A method. If you pay close attention, you will see that top middle is a bit larger than top right in terms of the area. This shows that its convergence radius is more, and it needs fewer number of iterates in order to converge. And it helps us. You will see that later in our numerical simulations. Okay, let me go on. Let me ask you a question here. Newton-Scholz iterative method. If you remember, I showed you the Newton-Scholz iterative method in order to solve the matrix sign function. Let me go back quickly and show you. This is it, number 27. 27 is the Newton-Scholz iterative method in order to find the matrix sign function. Does it converge globally? Is it useful? Let's see. The basis of attraction for this method. Try to pay attention to the left figure here. So in the left figure, there are clearly some area in the complex plane which is black. It says that according to the right figure, if you consider, for example, a large matrix that consists, for example, 1000 eigenvalues, if any of the eigenvalues locates on the black area, the Newton-Scholz method does not converge. And because of that, we say that Newton-Scholz method is okay, it's good. It does not need matrix inverse per computing step, but its convergence is local. It doesn't converge globally. Is there any question until now that I have to respond, Hemant?
Yeah, is there any question?
How about
Yeah, go ahead. Yeah.
How about how about Chiba chips? Is it global or local?
Could you ask your question again? Hey man, did you understand the question?
How about how about the Chiba chips? Is that global or local? The convergence of the Chiba chips.
Okay, I already told you that in this case, for the Newton-Scholz iterative method, the convergence is local. As you can see, in this figure, for example, the left hand side of the complex plane is totally blue and the right hand side of the complex plane is totally green. And because of that, you have global convergence. But in this figure, in the figure of Newton-Scholz, in the left-hand side of the complex plane, there is an area, there is a small area which is green, which is red, and in the right area, okay, there is a
I think there will be network issue or something.
Hemant, can I?
Yeah, there was a pause in between. There was a network issue at your side, I think. Yeah, I think Dr. Faiz has a network issue. I think that is a pause, right? Without, I think because there's
Yes,
no.
sir. Yes,
There's,
there is network issue.
yeah.
So
Mm,
we may contact again to Hemant sir, I think, to him through WhatsApp message. Let's see what is the response.
Man, can you hear me?
yeah, yeah. I think you have the network issue, right?
Yes, there was a problem with my internet. I'm sorry about that. I think I was disconnected.
Okay, yeah, yeah. Fine. Yeah, well,
Okay.
I can see you. I can see you now. Fine.
Okay. So can I go on?
Yeah, again, you share your PPT. Yeah, that is
Can
fine.
you see the slides now? Can you see the slides now?
Yeah, this is fine. I think here Dilan is asking the question. Chebyshev has a locally or globally convergence. I think this was the question related to Chebyshev.
Okay. All right. All right. For the Chebyshev method, I told you that. Let me show you. We have to check the global and the local convergence for our iterative method in each case according to A. So for some of the A's, the convergence is local, and for some of the A's, the convergence is local. This is the answer for the convergence of Chebyshev-Halley type family of iterative methods. And the point is, I want to repeat that. If you pay close attention here, for example, to this figure, top left for the Newton's method, you will see that the whole of the left half plane of the complex plane is blue, and the right half plane of the complex plane would be green. And because of that, the convergence is global here in this case. But in this figure, if you pay close attention to this figure about Newton shows the iterative method, the convergence is not any more global. Because if you divide the complex plane into two areas, the left area and the right area, in the left area, you will see that there are some black points, black region. And also in the right side. Because of that, if one of the eigenvalues of the input matrix be in the black area, then you cannot have the convergence and the method diverges. So Hemant, are there any other questions?
Yeah, one more question. Yeah, Saurabh.
Yeah, sir, can we that green and blue shade pictures about global convergence and these one. So what about the shades, sir? I missed that point. What does it mean that oval shaped regions?
All right, all right. You're talking about the shadows and the shades. You know, please now pay close attention to the top left figure. Okay, in the top left figure, you can clearly see a lot of shadows. You see, there are some lighter areas after that. When you move away from the roots, from the white area, the root, the exact root, you know, the areas would be darker and darker. Why is it for? It is because of the rate of convergence. For the Newton's method, the rate of convergence is 2. So you need to have more number of iterations in order to converge. But now please pay close attention to top middle figure. In the top middle figure, as you can see, you know, the region are lighter. It's because of its higher rate of convergence. So I told you that, for example, if you're in the first layer, in the first lighter area of the top middle figure, after one iterate of PM8 method, you will convert to the root. You will convert to the matrix sum function. If you move away, go to the second layer. After 2 iterates, you will converge. If you move further away from the root and enter the third layer, the third darker area, I hope you can see in your screens.
Yeah, yes,
you need
sir.
3 iterates in order to converge. Another thing that I pointed out is that we have PM8 and we have 3-4 PAD-A method. If you be quite careful and look at the figures, you will see that the top middle figure has a bit larger areas than top right figure. It says that top middle figure converts faster than top right method. That's the thing that I wanted to tell you. I will talk about these things later in simulations.
Yeah.
Anything
Okay,
else?
Thank you.
Anytime. Hemant, can I go on?
Yeah.
Okay. So let me just go on and okay, theorem. Convergence analysis. This part is important because you know in mathematics, especially in numeric analysis or computational mathematics, we need to provide convergence analysis or provide some theoretical things in order to support our findings. So you consider one more time that A is a complex matrix of the size n without any eigenvalues on the imaginary axis. So the sign function can be defined without any problem. It's well defined now. So this theorem says that the sequence of matrices obtained by our iterative methods converts to the matrix sign function as long as you consider the initial matrix x naught equals A. Okay, let me talk about the convergence analysis quickly. Actually, the convergence is based on the Jordan canonical forms. You know that you can consider your iterative method, your family of iterative method, as a rational operator. As a rational operator that acts on a matrix X and it gives us Z, Rj, Z inverse. So we know that the Jordan canonical form X equals Z, J, Z inverse is already given and we can write it. So it's now all about the rational map R. So you can consider your iterative method. Let me go back. For example, this iterative method, you can consider this family of iterative method, the right side, as a rational map. Okay, if you consider it as a rational map, then everything is about studying the eigenvalues. So xk to xk plus 1. So your map actually not only maps the matrix xk to matrix xk plus 1, it also maps the eigenvalues from the iterate k to the eigenvalues of the iterate k plus 1. So if you can find a relationship on the eigenvalues of the matrix iterates, then you can simply prove the convergence of your method. So you know that according to the Jordan canonical form, you can write down 45 for the matrix sign function. So matrix sign function here, before employing the matrix sign function, you have 45, yes. Z inverse A, Z equals to beta, that consists the Jordan blocks C and N. Those are appropriate blocks based on the Jordan canonical forms. And if you consider if you just name the eigenvalues which locates in the left-hand side and the right-hand side of the complex plane appropriately, then you have two clusters Please pay attention to what I'm saying. Then we have two clusters of eigenvalues. One cluster in the left side, one cluster in the right side. And you can write down the sign of A can be computed by 46. This is the definition according to the Jordan canonical form. This is not something new. From 47, if you write down the sign of the block matrix beta, then it would be the sign of Z inverse AZ, which according to some of the features of matrix function that I told you at the beginning of the talk, you can write down the right side of 47. After that, you can say that we have X nodes. X node is equals to A. So you can define the matrix D nodes and DK. And if you define this diagonal matrix, you can talk about the behavior of the eigenvalues for this diagonal matrix in order to prove the convergence of your iterative method. So number 48 is quite simple. It's nothing but rewriting the iterative method based on decay. Please pay attention to the features of matrix function. So you can obtain 48, and after that, as long as D node is diagonal, all of the decays are diagonal. Here we have to divide the rest of the proofs into two parts. In the first part, we can consider that decays are diagonal, and in the second part, we can consider that decay are not diagonal in general. Maybe for some matrices, those were not diagonal. So what can we do? In that case, we can similarly prove the convergence based on the eigenvalues. So here we can write 48, the last equation that I showed you in this slide. We can rewrite it as n uncoupled scalar equation. Okay. We can write 48 with n uncoupled scalar equations as follows. Number 49, alpha over beta. Okay, and as you can see here, dki is actually the element which is located on the diagonal of the matrix D in the case iterate. It's quite straightforward. After that, we have to consider number 50. If you consider for the scalar, now we tackle scalar things. You have to construct and write down dk plus 1 minus si over dk plus 1 plus si. You have to consider this formula. You have to write it down, and you have to try to simplify your structure. After a couple of simplifications that I didn't provide here for the sake of simplicity, you can obtain the right side of 50. In the right side of 50, you can clearly see that there is a power 6. There is a relationship between the case iterate and k plus 1 iterate, and this relationship depends on a factor to the power of 6. This 6 shows the rate of convergence later in our work. So under some conditions, you consider that the sign of any lambda, lambda is the eigenvalue of the matrix. So the sign for scalars are plus minus 1. And under some conditions on the multiplier in 50, you can clearly write down 51, which shows that when k tends to infinity under an appropriate initial matrix, number 50 tends to 0, and it shows the convergence, and dki converts to plus minus 1. The other part of the proof, I told you that decays are not diagonal or based on the eigenvalues of the matrix. There is a similar relationship, and actually, you know, your iterative method maps the eigenvalues from the k iterate to the k plus 1 iterate. And because of that, this part is quite simple and similar. Let me skip it. And at the end, you can have the convergence, even for the general case that dk is not anymore a diagonal matrix. Okay, next slide. This slide is about derivative convergence. It is important for us to write down what is the convergence order. Under same assumptions as in the previous theorem, we can write down the convergence order of our family of iterative methods, which is at least 6. Here I wrote on purpose that derivative convergence is at least 6. I will tell you why. So the way of proving the convergence rate is based on considering several facts. For example, if you remember, I told you that if A commutes with A and f of A commutes with each other. So S is a matrix sign function. So S and A commutes with each other. The second thing is that when you want to compute the convergence order, you are in the convergence phase. So in the convergence phase, xk is quite close to S. So you can approximately replace xk by S. This is another important thing that you can use. There are some other features that you can use based on 55. S to the power of 2 is equal to I. Let me here ask you a question. Why did I write down S squared equals I? Can anyone tell me here? If you would like to answer my question, I will be happy. Hemant, do we have any person to respond me for this simple question? Or
any reply to the question?
Or they prefer to listen?
Yeah, why S square is equal to I is the question. Right, sir?
It's simple, yeah. If you remember, we are trying to find the solution to the matrix equation x to the power of 2 equals I.
Yeah.
So S is the solution. So S satisfies the nonlinear matrix equation. So S squared equals I. This is one thing. This is quite simple. The second thing is simple as well. S inverse equals S. If you multiply both sides of S squared equals I by S inverse, then you obtain the second one. And if you generalize these two things, you will obtain the third and the fourth formulas in number 55. Okay, I think these theoretical parts are not that more interesting for the attendees for now. Let me just move quickly. If you consider 56 and after some simplifications, you can obtain 58. So in 58, under an appropriate matrix norm, we have obtained a bound for the difference of the xk plus 1 and S, which shows that the convergence order is 6, as long as the norms in the the norms in that parenthesis are bounded. As long as that norm is bounded, or those two norms are bounded, so the convergence rate is 6. And here, please pay attention that the convergence order for some cases is not anymore 6. The convergence rate is 8, for example. If you consider A equals 1, then we have 8th order of convergence, and we can obtain the error bound, the error estimation 59. This is not in contradiction with the iterative method that we proposed in order to solve nonlinear equations. If you remember, that iterative method was of 6th order of convergence. So I hope at the end of the talk someone asks about this question or tell me the answer, that how we obtained 8th order of convergence. Okay, let me go on and now talk about the stability. Okay, the stability. Questions? Do we have any?
Yeah. Question. Yeah. Yes, Monish sir.
Yes, Faisal, I have one question related to the order of convergence. Like in equation number 59, we have seen that the power of xk minus s norm is 8. So when we transform any any iterative method for solving any scalar nonlinear equation to some method for solving this nonlinear equation, so is it always mandatory that the previous order is retained when we convert it into the matrix form?
Can you please repeat the last part of your question?
Is it always necessary that the previous order is always retained when we convert our methods to the iterative forms?
Okay, if I understood you properly, the convergence order is at least the same as the convergence order for the scalar case. Okay, but sometimes the convergence order could be higher than that, and for that thing you have to write down number 59. You have to pursue this process 55, 56, 57.
Okay.
You have to write down this process for a specific A. For the general A, it has 6th order of convergence. But for some specific choices of A, you will see that the convergence order will passes from 6 to 8.
Okay.
That's
okay.
The thing.
Right. Thank you, sir. Thank you.
Anytime. Sometimes you. Okay.
Okay. Fine. Any other question? I think there's no question.
Okay. Can I go on?
Yeah.
Okay. Let me just quickly go on. Stability. Iterative methods that are unstable are not useful for us. One simple sentence. We have to find the stable iterative methods. Hopefully, the iterative methods for finding matrix sign function are stable asymptotically. This means that if you consider a small perturbation, such as delta k in the case iterate of your iterative method 34, then you can perform a first order error analysis and shows that when you move along the iterates, the magnification of error can be controlled, okay, by some bounds, such as 61. In 61, you can clearly see that the error can be bounded by some value. If you consider, if you just take some norms from 61, you can obtain an error bound for the stability, and because of that, the stability in this part is asymptotic. Okay, some numerical results. Here I considered 12 randomly generated matrices of different sizes. For example, 100 by 100 up to, I think, 1200 by 1200. And I tried to compare the behavior of different numerical methods in order to solve and find the matrix sign function. Okay, Let me go on to the next page and see the results. Results of comparisons based on number of iterates. Okay, for example, let me tell you, for the size 100 with 100, this is random digit. Newton's method requires 15 iterations in order to converge. PM8 requires 5. Kenyan lob method of order 8 requires 5. Kenyan lob method of order 6 requires 6 iterations. PM4 method requires 5 iterations to converge. You can clearly see. But please take a look at the last row of this table. The mean for the number of iterations in order to converge. When we increase the size of the input matrices, you can clearly see that for the Newton's method, it has around 20 iterates, but PM8 requires the minimum number of iterations in order to converge. Why? If you remember the attraction basins that I showed you ago, this is because here, one more time, take a look at the attraction basins of PM8. Okay? For PM8, the attraction basins are larger and lighter than the other compared methods. This shows that they converge quickly or faster than the other competitives. Go back. So this is about the number of iterates and about the CPU times. What about the CPU times? If you one more time pay close attention to the CPU times, yes, sometimes some of the referees or some people will ask you, all right, this method converges faster, it converges globally, you studied its convergence, its rate of convergence, but is it useful in terms of CPU time? You have to respond. If you pay close attention to the last row of this table, which are the results of comparison for CPU times, you will see that the mean for the CPU times of PM8 is less than the other ones. You know, for the Newton's method, even for KLM 8 method, the CPU time is more than what you can see for the PM8. And because of that, you can clearly write down that our method is useful in practice. However, let me here also tell you that the CPU time, when you compute matrix sign functions based on iterative methods, heavily depends on the choice of the stopping criterion. Sometimes, you know, the best stopping criterion is that the xk squared minus identity matrix is less than something in terms of its norm. And this is most of the time the stopping criterion. And so this is another thing. Please consider the case 100 by 100. Please consider the 100 by 100 input matrix. At the beginning, pay attention to the top left figure. In top left figure, you can clearly see the eigenvalues. The eigenvalues have been distributed in the complex plane. But let's see what will happen after the first iteration in order to solve matrix sign function. When you impose one iterate, the eigenvalues will try to be clustered. In the second phase, they will be more clustered. X3 in top left figure, only 1 or 2 eigenvalues have not yet being clustered. But in X4 and X5, you can clearly see that the eigenvalues have been clustered around -1 and +1. This is the job and the career of matrix sign function. It is a function to cluster the eigenvalues of the matrices in each part of the complex plane, the left part and the right part. All right, and the last slides about future works. You may say that what can we do in this field? Of course, it's interesting to design and construct efficient schemes for a matrix sign function, special matrix sign function. After that, it is important and useful to extend the efficient existing iterative methods for matrix sector function and the other matrix functions, such as matrix square root. This is another field of study. What about the other things? For example, matrix geometric mean. If you have two scalars, A and B, you can clearly write down its geometric mean. Well, have you ever thought what would be the matrix geometric mean when you face with two Hermitian positive definite matrices? So in such cases, one more time, you have to propose iterative methods based on matrix sign function. Another field of research is that can we generalize the existing solvers via the concept of Moore-Penrose inverse? Because in most of the iterative methods that we understood until now, we used one matrix inverse per computing cycle. What if we replace it with Moore-Penrose inverse and we relax the assumption of having eigenvalues on the imaginary axis? What will happen then? Another field of research is to find the action of matrix functions on vectors. This is very much important when you solve practical partial differential equations, especially time-dependent partial differential equations with method of lines, because with method of lines, the time-dependent partial differential equation will be simplified to a system of ODEs, ordinary differential equations. And you need to compute a matrix exponential. And at the end, the question is there any application of matrix function in financial mathematics? Yes, there is. Can we talk about that, for example, in portfolio optimization? For example, in option pricing, sometimes we face with some matrix function and we have to cope with them. Okay. The last slide is about references. The most important reference here is reference number 2, the book by Professor Nicholas Hyam, Functions of Matrix Theory in Computation, published in 2008. Hopefully I have the book with myself here and I can show you. This is the most useful book that I've ever met in this field. It has many more issues about matrix functions inside it that you can read and enjoy. Okay, thank you. That's it for now. If you have any questions, I'm here to reply. Thanks for having me.
Thanks for your talk. Any question before I proceed? Yeah, question from the participant, question from our panel member. Means all those who are having any question, is a good time to ask the question.
Yes. Any questions about
yeah. Okay. Dylan, you can go ahead for the question.
Dear Dr. Fazullah, is there any problem with the principal part and the other part, non-principal part of the matrices, especially when we have a rectangular matrix?
We define functions and matrices for square cases, not for rectangular cases. So your question is a research question. We need to think about it more, study more, and see what we can do.
Okay. So
Yeah, that's all, Dilan, or any question?
I have one question also for you.
Yeah.
Maybe get the record by the email.
Yeah, we'll try.
Okay, thank you very much. Thank you.
Yeah. The content we are having, so maybe the size will be different. Yeah, size.
Thank you, Dr. Fazullah. Thank you for you.
Thanks for everything. Thanks for participating in the talk.
Yeah. Next question. Manish sir.
Yes, sir. Sir, my question is, like, we have certain analytical methods for solving, let us say, right? So are there any analytical methods available for solving these nonlinear matrix equations?
What do you mean? Can you describe your question more?
For calculating the pseudo inverse of any matrix, we do singular value decomposition. We can use QR decompositions. So those are all analytical techniques. And similarly, we have certain limitations of those analytical methods, and then we jump to the iterative methods to get the better solutions.
No. I actually here we do most of the time we do not use SVD decomposition, but I told you that we use Jordan canonical form, short form, or the Hermite interpolation in order to find a solution theoretically. The point is, in some cases, as I told you, when the entries of the matrix change by time, and you have a lot of matrices that you have to compute their corresponding matrix functions. So using the theoretical methods is not recommended, and it is better to consider iterative methods. That's the reason.
Right. Thank you, sir.
Anytime.
Yeah. Next question, Saurabh.
Sir, when you're saying that stabilized solution, stabilizing, the case of stability. So how does it is it connected to positive definite solution, and if so, why?
No, it's not related to positive definite solution. Maybe you are talking and you are seeing the procedure in a general nonlinear matrix equation format. Here we focus on matrix sign nonlinear matrix equation. That's the the nonlinear matrix equation that I showed you at the beginning. This one, number one. So the solution to number one is not necessarily positive definite. And under any cases of the solution matrix, the iterative method under the given assumptions could be stable, especially asymptotically.
Okay, sir. Thank you, sir. Thank you.
Anytime.
Any question? Any other question?
I think someone, Saurabh asked the
question. He asked, yeah. So, any other questions? So, okay. So I think there is no question.
Yes, sir. I have one last question, Professor.
Okay.
One last question, sir. Are there any methods to choose the initial approximation here? Like we choose initial matrices X0 to start the iterative method. So Like in scalar case, we have certain techniques to find out the initial approximation. So similarly here, if we want to start the iterative process, so we choose x naught is equal to a. So is there any efficient way here to choose this matrix, initial matrix?
That's a very good question. First of all, x naught equals 8 is a very popular, useful, and good initial approximation. So with this initial choice, the iterative method converges without any doubts. But the point is, yes, there are some techniques in order to accelerate the iterative method in each iterate based on some scalings. Sometimes we have norm scaling, determinantal scaling, inverse scaling. There are 3 types of scaling that you can accelerate the iterative procedure. As well as some people try to find out, a better initial choice. The better initial choice is based on the multiplication of a multiplier to the matrix A. For example, alpha A. Alpha A would be the initial matrix, and alpha should be chosen properly. If you choose it properly, yes, it helps you to converge faster.
Okay. Thank you, sir. Thank you.
Anytime.
So I think this was the last question. So I would like to thank Soleimani for giving you a time to 2 hours. Get up in the morning and now come for the talk. So thanks for accepting invitation for this workshop. So this was the initialization of the talk and gathering. So hopefully this year in July somewhere we will plan for the big workshop or the conference and meet person. We'll try. Let's see.
Okay. Hope so. Yeah, of course. Thank you so much. It would be a pleasure.
Yeah, all the things are going normal, so we can go with an physical mode.
Yeah, hope so. Thanks for everything. Thanks for inviting me for the talk. And even after the talk, if any of the attendees or the people who will see the videos after my talk, if they have any types of questions about the numerical linear algebra, I will try my best in order to respond them even with my emails. So feel free to email me if you have any types of questions.
Okay, thank you, sir.
Thank you. Thank you.
So we can move to the next speaker. I think